Great. And I'm going to open up the first lecture. And view slideshow. Zoom, share screen. Okay, can everyone see my screen? Yep, excellent. Okay, so semantic security. This is kind of the most basic notion of security that we're going to get into during this class. So let's start with the basics. So overview of security and kind of what our motivations are in cryptography. Let's say Alice and Bob share a secret key K. And Alice wants to send a message M to Bob through an untrusted medium. This is a medium where it's possible that someone might listen in on the message and see the message. Now, the mechanism that we're going to demonstrate in this lecture is Shannon ciphers as a method of encrypting messages. So with that, let's get started. So first, who is Cloud Shannon? This is the Shannon of Shannon ciphers. He is widely considered to be the father of information theory, which has implications in both computer science broadly and huge implications in cryptography specifically. He was friends with Alan Turing, and they actually compared notes on Turing's famous paper, The Universal Turing Machine, which is just mind-blowing that they actually talked about that. He was an avid chess player and actually estimated the complexity of chess to be 10 to the 120, which is still what's referenced today when we talk about chess complexity. And more importantly for this class, he was the first to formalize the notion of security. He was, a very incredible mathematician, and he built a lot of the building blocks we use for our security. So a lot to thank him for. So with that, let's talk about the Shannon cipher. So a Shannon cipher is a pair of functions, E and D. Now, you see this little epsilon notation on the left. That's just a way of saying the system, the encryption system, or the cryptography system. Now, the encryption function takes two arguments, a key K and a message M, and it outputs a ciphertext C. So as you can see, the encryption of K and M is what C is equal to. And the decryption function, or the D function, takes in two arguments as well, a key K and a ciphertext C, and it produces a plain text M. While the encryption function may be random, the decryption function must be deterministic. And here's an example of how the decryption function works. M equals D of K comma C, where K is the key and C is a ciphertext. Any questions about these functions? This is kind of the two most basic building blocks of cryptography. So I really want to make sure we feel comfortable with these ideas. So I'm looking in the chat just for a couple of seconds. Is determinism the same as a one-to-one function? That's a great question, Abrar. So determinism is not the same as a one-to-one function. Determinism says, given an input, you will receive a consistent and the same output for that input. So the way to think about that is if I input 5 into a function and the output is 3, every time I input 5, I should receive 3. A one-to-one function is every input has a unique output. And that's generally expected with ciphers, but that is not what deterministic means. Are there any other questions about these kind of building blocks of encryption and decryption? All right, I'm not seeing any in the chat and not hearing any aloud. Remember, you can always speak up aloud during class. Don't be worried about interrupting me, but I know sometimes the chat feels more comfortable. So we'll keep moving on. So the correctness requirement for a Shannon cipher is that decryption must undo encryption. Now, I'm kind of curious, does anyone have any ideas about how we might express this concept mathematically? So given these two functions, how would we express mathematically that decryption can quote unquote undo encryption? Any thoughts on this? I'm keeping an eye on the chat. I'll kind of give us 30 seconds for everyone to ideate and think for a little bit. Like dividing and multiplying being opposites. Yeah, so if you had A times B equals C, then you could undo the multiplication with a division by saying C divided by A will yield B. That's a great question. Mara Glenn, I see inverse functions. That's a good idea, but doesn't exactly apply here. Abrar, solve for plain text functions. Jared, you would show that M remains the same for E and D. Those, you both are getting right on that right idea. Mara Glenn, inverse functions are an excellent idea. However, that's not exactly what this concept is. So decryption must undo encryption. So to take the idea that Jared and Abrar were sharing with us, M equals D of K, E K of E of K of N and M. And if we kind of look back to the previous slide, we can see that C is a ciphertext, and all that does is that it substitutes the ciphertext for what generates a ciphertext, which is the encryption function. And I'm also going to define this encryption system a little bit more formally. So let's let K be the key space, M be the message space, and C be the ciphertext space. The encryption takes K and M, performs an operation on them, and produces the ciphertext C. D takes this key K, takes the key space K and the ciphertext space C, and produces the message space M. Now you're seeing the X there. I know normally that X indicates multiplication. However, in this class, when you see that X in this kind of notation, all it means is some kind of operation is being performed. And the general cipher is defined over the key space, the message space, and the ciphertext space. So any questions on this slide and its notation? This is when I first saw this concept, I remember it being quite confusing for me. And so I want to make sure I give you all the time you might need to process it and think about it for a moment. So I'm kind of checking, monitoring the chat for any questions over the next 30 seconds. Okay, it seems like everyone's feeling comfortable with that, so we'll keep moving. So let's revisit the one-time pad from the previous lecture. Now, can anyone speak up and remind us of how the one-time pad works? Alternatively, you can also message in the chat if you don't feel comfortable speaking aloud. Great, James and Abrar, thank you. You exclusive for the message in the key or performs a binary mask, both great responses. So we're gonna take that one-time pad we discussed last class and where we defined it rather casually. And I'm gonna define it much more formally using this math notation. So a one-time pad is a Shannon cipher such that the key space, the message space, and the ciphertext space are all 0, 1, representing 0 and 1 bits of length L, where L is the possible length of the message. The encryption for a key K sampled from the key space, or 0,1L, and given a message M, where the message is sampled from the key space, from the message space 0,1 of length L, the encryption of K and M is considered to be K exclusivor M. The decryption for a key K and a ciphertext C is the exclusivor of the key K and the ciphertext C. Now, in a future homework assignment, not homework 0, but a future one, we are going to ask everyone to write out a mathematical justification that the one-time pad meets the earlier correctness requirement, i.e. That decryption undoes encryption. Don't message that in the chat right now or in the Slack, but just so you all know, that's going to be a future homework question. Any questions on the one-time pad and how I've laid it out in this more formal notation? Is L clean star? Abrara, can you elaborate on what you mean by clean star? While I'm waiting for them to reply. L is simply the length. So commonly, L might be 128. That means it's 128 zeros or ones in series as a string. The language wall combinations of 0 and 1. Yes, that is a good way of thinking about this. Okay, so let's talk about some of the security requirements that we're going to spend thinking about. Let's begin with the key assumption that adversaries know the encryption mechanism and the distribution of the key space K. If Alice encrypts a message M with a key K and an adversary obtains the ciphertext C, the key K needs to be hard to guess. If the key K is easy to guess, then the adversary will just brute force until they discover K. Therefore, K must be chosen uniformly and randomly from a large key space K. The second security requirement is that adversaries may have some knowledge of the message being encrypted. And I think it's easy to see how this plays out in real life. Here's an example. Let's suppose you want to send one of two messages, meet at lunchtime or meet at snack time to meet with a friend. Our adversary from the outset has a 50% chance of guessing correctly, whether or not you intended to meet at lunchtime or whether or not you wanted to meet at snack time. They have a 50-50 shot at guessing that correctly. A secure ciphertext should not increase the probability of guessing correctly. Or put another way, if the adversary saw the ciphertext, they shouldn't be able to improve their odds of guessing correctly. However, let's suppose there are 90 keys K sub 0, such that the encryption of K sub 0 and M sub 0 yields ciphertext C. And there are 10 keys K1, such that the encryption of K1 and M1 also yields C. Well, armed with this information, can anyone in the chat tell me the new odds of the adversary correctly guessing which message was sent? I'm going to pause here for another 30 seconds and wait for something in the chat or something audibly. So keep in mind the original odds were a 50% chance of correctly guessing M0 or M1. And now we have this new distribution of keys that is not a 50-50 distribution. So how does that affect our ability to guess? %, Azan, that is absolutely correct. So to kind of outline how we arrive at the probability of 90% is that it's 90 over 90 plus 10 for whether or not the given message is M sub 0. Therefore, if you're an adversary, you have a 90% chance of guessing correctly what the message is. Now, any questions on security requirement 2 that we need to assume that the adversary may have some knowledge of the message being encrypted? Or security requirement 1, adversaries know the encryption mechanism and the distribution of the key space K. I'll wait another maybe 15, 20 seconds for anyone to think about this. Okay, we'll keep moving on then. So let's talk about perfect security. So perfect security carries this assumption that a key is drawn uniformly and randomly from a large key space. When a key meets these requirements, you might see it notated as a bold K. Therefore, let's kind of go back to our classic Shannon cipher definition, defined over K, M, and C. If for all messages where you have message 0, message 1 in M, and for all ciphertext in the ciphertext space C, and for all K sampled uniformly and randomly. Now, a brief pause on notation. If you see the arrow with the R above it, that's equivalent to saying sampled at uniform and random. You might see that and the bold K either in conjunction or separately. Both mean that the key was sampled at random and at uniform. So the probability that the encryption with K and M sub 0 equals C and K and M sub 1 equals C, those are equivalent probabilities. And this definition of perfect security, the intuition behind it is that given a ciphertext C, you can't really guess what message was encrypted with it. Does that make sense? I think this is a pretty key thought, the idea. I mean, this is kind of the notion of security that we're going to carry with us through the entire course, is this notion that given a ciphertext C, you can't tell what the original message was. So are there any questions about this probability, about what it means, about the notation, about what uniform random means, about the message space, key space, anything at all? I want to take a moment and check for questions. So we're going to wait 45 seconds for questions over here. You might occasionally see for all notated as an upside down A. The uniform random part. So uniform randomness means that if you think about a normal curve, about the normal distribution, it has that kind of big bump in the middle. So if you just picked numbers from a uniform distribution, there's a good chance, like your numbers, there's a probability that I can understand which number you picked. That's different than sampling from a uniform random distribution where it will look more flat. So I have no information about the key. I cannot infer anything about the key you generated with any sense of probability. The probability you drew K0 or K1 is equivalent to me. That's what uniform random means. And can I repeat what the equation means again? So what this equation means is that the probability that the ciphertext C was generated using a given key K, the probability that it was message 0 as a second parameter or message 1 as a second parameter are equivalent. This is saying that there is no way to tell, given a ciphertext C, whether message 0 or message 1 were used to generate it. So I think those are the two questions. So we're going to continue moving forward. So a result of our definition of perfect security is that given a uniformly randomly sampled K, the encryption of that K in a message M is a ciphertext C, and that's going to equal some number of possible ciphertext C. And if we look at this definition of perfect security in the context of one-time pads, for any message M and ciphertext C, K exclusive or M equals C. Therefore, NC equals 1, satisfying the above result. And because this definition of perfect security is derived from the initial definition of perfect security, then we know that the one-time pad meets perfect security. So I understand that this might be a slightly unfamiliar notion, and I'm not going to discuss how you derive this security notion from the one-time pad. I can go over that maybe in office hours or at another time. But the really important part of this is that I wanted to show you kind of somewhat formally why the one-time pad achieves perfect security. So this is a great notion, perfect security. But as with all things perfect, we should be a little bit suspicious. And here's kind of a problem that might exist with perfect security. So let's kind of go with our classic Shandon cipher. If this cipher is to be perfectly secure, then the size of the keys must be greater than or equal to the size of the messages. Now, the reason this statement is true is that if you have less keys than messages, we're going to be violating that definition of perfect security we discussed earlier. And I think it's pretty clear why this is not a very useful definition. Sorry, not a very useful definition for security. It's impractical to have keys as large as the size of the message we're transmitting. I mean, if you can transmit a 10 gigabyte key, why not just use that mechanism to transfer the knowledge itself, or for anything? If you can transfer the key and the key is as large as the message, it's equivalent work to transfer the message and the key. So why not just transfer the message instead of the key? So it's very impractical to have keys that are at least as large as the size of the messages we're transmitting. And if we're thinking carefully about this, I'm not that concerned about, perfect security. What I really care about is I know that I have computationally bounded adversaries, right? I know someone's trying to hack a message that I sent, and they are limited by today's computing power. And so if it takes them 10 years to calculate the message, well, to me, that is strong enough security. And so with cryptography, a lot of our work is centered around computationally bound adversaries. And another thing we're interested in is efficient algorithms for encrypting and decrypting. So if you can encrypt something perfectly, but it takes 5 years to encrypt it, well, that system is not very useful. Similarly, if you can decrypt the same message and it takes 5 years to decrypt, well, that's not a very useful system either. So are there any questions on some of these problems with perfect security? I'm going to wait another 30 seconds to a minute, just kind of holding the space for any questions. Can you elaborate more about the key needing to be more than the message? Sure. So this is a proof that follows from the definition of perfect security. And once again, I'm trying to keep this course light, so I don't want to go into the mathematical details of this proof, but we can absolutely do that during office hours. I'd love to go through that with you. But the concept is that if you have a message, if you have a key that's shorter than a message, well, all of a sudden, the probability that for a given key and a given message that it produces a ciphertext C, well, there's going to be some combination of those that is not possible. And when that's the case, all of a sudden, you have information about about whether or not a given message is a given ciphertext. And so you can imagine a scenario where you as an adversary can just send that message that breaks security and another message and ask for the encryption back, and then that'll tell you which message, which encryption was used. So does that help? Does that help answer the question? When I'm talking about efficient functions, yes, I am discussing the time complexity of the functions. So at the bottom, you'll see I said by efficient, we mean polynomial functions. These are functions that run in polynomial time. The concept of polynomial time versus non-polynomial time is you can think about this as running less than exponential, for example. This is following the same notions of big O notation that you might have experienced in another class.
Can you hear me?
Yeah, I can hear you.
So the K, like the key space, that's just like the set of keys.
Yes. So if a key is longer than a message, then by necessity the key space must be larger or equal to the message space. Does that make sense?
Yeah, and by the size of the key, like an example, like if you have like a 10 character key, right, and the message is 10 characters, that would be like the size that you're mentioning.
Yeah, that's exactly correct. Yeah,
Okay, so if the size of the keys are greater than the size of the messages, then the key space must be greater than the message space.
that's exactly right. Yeah.
Okay, all right.
Does that intuition make sense, or should I kind of review that maybe more closely?
I'm not sure as to why that's the case.
Okay. So let's take a moment and let's pause. And I think I'd like to spend some time flushing that out so everyone feels comfortable with that idea. So let me grab an annotation tool. So let's say I have this rectangle, and this rectangle represents represents a key. And this rectangle, the bottom rectangle, represents a message. Is everyone kind of following? So the top bar is a key, and the bottom bar is a message. There's any questions about that piece? Okay. So if you think about an individual key being as large as the black bars, if you take every individual line in this black bar and represent it as a 0 or a 1, all of the possible keys, well, there's going to be more options. It's going to be 2 to the length of the key as a total number of possible keys. And for the message, it'll be 2 to the length of the message for all of the possible messages. So do you see in this case how a longer key necessitates a larger key space? Does that feel does this visual help that intuition feel more clear?
Yes.
Okay. Is anyone else feeling like they want to think about this a little bit more? Okay. Thank you for the question. I really appreciate you asking that out loud. That's very brave. And that was a great question. That's a difficult concept to understand. So I'm glad we spent some time clearing that up. So let's actually, we're about to dive into semantic security. Let's take a quick 5-minute break. So I have the time at 6:19 now. So at 6:24, we'll reconvene class. But I want to give everyone a 5-minute break. And I'm gonna take a break as well, but in a minute, I'll come back and answer some questions. All right, everyone. We're back. Andrew, I saw you asked a question. Would the keycat 256 fall under that rule? And I think the rule you're referencing is that the key space must be larger than the message space. And that's a great question. So the keycat 256 design is a hash function, and it can be used for encryption and something called pseudo random number generation, which we're going to get into in a moment. And so it is kind of a different, almost think of it as almost a separate concept from this idea of key space and message space, right? When you have a pseudo random number generator, you kind of pass it a small key to generate a large key. And so in some sense it does apply. In other senses, it's not a perfect fit. Does that answer your question, Andrew? About keycat 256? Yeah, so the output is a similar length from the function, but the input's not always the same size. And actually, Andrew, that's a great question. We're going to get into the pseudo random number generators later in the lecture. So with that, semantic security. Also, Andrew, please don't. Yeah, excellent. I was saying, please don't feel sorry for asking any questions. Everyone, please ask questions, no matter how silly they or simple they feel to you. When I first took this class, I had a lot of questions. So I'd like to encourage questions. Okay, so
Hello.
yeah,
I'm sorry. Could you like repeat one more time why the key space must be greater? I kind of just like lost my thought.
yeah, totally. Um, so if the key space is smaller than the message space, the intuition is that there's going to exist some key message ciphertext combination where that ciphertext is not possible given a key and a message. And the result of that is that if you know that ciphertext, and remember, one of our assumptions is that the adversary understands the key space a distribution and the actual mechanism. If you know which message doesn't work, then you can use that information to break the security of the system. Does that feel like that? Does that intuition make sense to you, or does it not feel clear to you
It
still?
makes sense. Thank you.
Yeah, and we're going to get more into that. That's a great question. And we're going to get more into that security actually later in this lecture. So that's a great foreshadow. Okay, so semantic security. So the intuition of semantic security is that the probability that a computationally bounded adversary can learn anything about a message M given its ciphertext C is negligible. Now, the one exception to that is the actual length of the message. And we won't get into that during this lecture, but later in the course, we'll go through why it's difficult to hide the message length. So the way we define semantic security requires my favorite part of this class, and that's talking about security games. And the semantic security game is generally defined as follows. So there's an experiment B. B is either a 0 or a 1. Let the cipher, so let's define a Shannon cipher or a cipher, and let's let our adversary A be computationally bounded. So those are our two starting assumptions. The adversary is going to pick two messages, M0 and M1, from the message space M and send them to a challenger. The challenger receives those two messages and then selects the K uniformly randomly from the key space. The challenger then computes the encryption of the key and M sub B, where B is the experiment bit. So remember 0 or 1, and computes C, and then sends C to the adversary. The adversary outputs B star, which is the adversary's guess of which experiment was selected by the challenger, or maybe more clearly, which message was encrypted by the challenger. Are there any questions on this game and how it works? Jared, your question on reusing keys. It wouldn't necessarily be reusing keys, but maybe focusing on semantic security for now. Any questions on this game and how it works? Okay, great. So the way we're going to define semantic security is going to involve something called the semantic security advantage. So the semantic security advantage of an adversary A is defined as this. It's the probability that A outputs 1 in experiment 0 minus the probability that the adversary outputs 1 in experiment 1. And theoretically, if the adversary could break the encryption scheme, the W0 probability would be 0, and the W1 probability would be 1. However, if the adversary knew nothing about the security, then the probability would be uniform for both, and the difference would be 0. So kind of just at pure random, adversary A has a probability of outputting has a 50% chance of getting the probability of outputting the correct bit, giving them an advantage of 0. In order to be semantically secure, that advantage lambda has to be negligible. We can kind of think about this mathematically as such that 1 plus lambda should be like roughly equal to 1. Does that make sense? I'm going to pause here because there's a lot of concepts on the slide that might feel new. So we'll just take a minute and think for a moment about these concepts. So talking about the probabilities and the concept of what is negligible and experiments 0 and 1. So I'm going to pause here for 1 minute and kind of keep an eye on the chat or listening for any questions.
If W is a probability, then are we finding the probability of that probability?
Yeah. So that's a great question. The way this notation is expressing it is WB is whether or not the WB is whether or not is like maybe more formally whether or not the adversary guessed the correct bit in experiment 0, and W1 is whether or not the adversary selected the correct bit in experiment 1. So the probability of whether the adversary selected the correct bit in experiment 0 is how we should technically be reading PRW0. Does that make a little bit of sense, or does that still feel a little bit hazy?
I'm still a bit confused.
Yeah, okay.
Yeah.
So W0, what I've highlighted there, is whether or not the adversary correctly. So I understand on the slide I made a notation mistake, right? I said WB is a probability that A outputs 1 in experiment B. What that should really say, and I'll make a correction here when I go through the slides later, is that WB is actually the probability that the adversary correctly guesses the correct output in this scenario.
Okay, that makes a lot more sense.
Yeah, sorry about that. Abrar, if you want to claim extra credit, you can drop a link. You could do the anonymous feedback form or through Slack. Message me, and I'll give you a point or two for that. Does anyone have any questions about this concept of probability and how it applies here? Another note, these bars are representing the absolute value. Okay, we'll keep it moving then. So let's actually take this semantic security, a very abstract and a very dry concept, and let's go ahead and derive something useful from it. So semantic security guarantees that an adversary cannot recover a message from ciphertext. Put another way, if a cipher is semantically secure, then we can guarantee that an adversary cannot recover a message from the ciphertext. Here is our security game for message recovery. Let epsilon be our semantically secure cipher defined over KMC, and let our adversary A be computationally bounded. The challenger will sample the random key, sample the random message, uniformly random, and compute the encryption and generate the ciphertext C, and then the ciphertext C to the adversary A. The adversary A will output the message M star, where the message M star is meant to be a guess at the original message. So any questions on the security game and how it works? Does it make sense why if you can beat the security game, then we know you can recover the message correctly. And we actually can guarantee that if you can beat the security game, we know you can beat this. It's not like there's a system of beating this message that wouldn't be able to beat the system. So any questions on this whole concept? All right, great. So we're actually going to add a nice layer of complexity, and we're going to use, so let's say somehow this adversary was able to guess the correct message. Well, what we're going to do is we're going to say, if the adversary can beat the message recovery game, then we know the adversary can beat the semantic security game. And since we know that a computationally bounded adversary cannot beat semantic security, therefore we know that a computationally bounded adversary cannot recover the message. So let's kind of go through these concepts. So similar system, let E be a semantically secure cipher defined over KMC. Let our adversary B be computationally bounded. Adversary B will sample M0 and M1 and send it to the challenger. The challenger will select a key at random, compute the ciphertext C, and send C back to B. B will then send ciphertext C back to A. This is simulating the message recovery game. A will return M star. If M star equals M1, then the adversary B will return 1. Otherwise, return 0. So what's happening here is we're saying, if you can beat the message recovery game, then you can beat the semantic security game. And since we know you can't beat semantic security with a computationally bounded adversary, then you can't recover a message that's been encrypted with a semantic security scheme with a computationally bounded adversary. Do those concepts, are they connecting for you? Does that feel like, and please, like, let's take some time here. This is a lot of concepts tied together for the entire lecture so far. So I want to make sure we take a moment and get this right. Any questions? I'm going to pause for 1 minute here.
I messaged the chat. I just asked, like, can you repeat what a computationally bound adversary is?
Yeah, great question. So a computationally bounded adversary is an adversary that is limited by like modern computing techniques. So the way to think about that is if an adversary can crack this message using like the NSA's fast computers, then they're considered computationally bounded. If it would take them 20 years to crack our cipher, well, to me, that would be considered computationally bounded. That means that it's secure if it takes 20 years to crack it with the computer.
Okay.
Does that intuition feel clear to you?
Yes, it does. Thank you so much.
Yeah, great. Any other questions? Looking at the chat. I see that question now. Thank you for verbalizing it. All right, we'll keep on rolling. Yeah, so therefore, if we can recover the message, then we have broken semantic security. So this is kind of a really cool application of semantic security. So let's do something kind of fun and derive anonymous routing from semantic security. So suppose Alice wants to send a message to Bob, but doesn't want Bob to know that the message came from her. An example, you want a radiologist to review a patient's medical scans without revealing the patient's identity. Well, first, Alice must share a key K0 with router 0 and a key K1 with router 1. And these keys are sampled from the key space we defined at the top. Then Alice sends the encryption of K1 in the message using K0 to router 1. Router 1 decrypts and then sends the message EK1M to router 2 in random order. This is assuming router 1 is receiving multiple messages and is re-randomizing them on the output. Then router 2 decrypts and sends the message M to Bob again in random order of the messages that's coming into it. Well, Alice's security is 1 over n, where n is the number of messages sent along the network, right? The probability Bob can guess which message is Alice's is 1 over n under this schema. Does this concept kind of make sense? This is called a mixed net, by the way. If you remember actually in the first lecture, a mixed net was one of the first concepts we discussed in class. So I'm going to pause here for like 30 seconds and kind of wait for questions, if anyone has a question.
So is a router just like sending the message to another encryption function?
Yeah, think of the router as like a kind of like almost like someone handing things off. So if you think about this as handing off envelopes, right? I hand a sealed envelope to router 1. Router 1 opens that sealed envelope and takes that inner envelope and hands that to router 2. Router 2 opens the inner envelope and hands the message to person B. That's a great way of thinking about routers.
So the router would send that envelope and then I guess encrypt that message once more?
Yeah, so something, if you were actually to implement this, right, router 2 would have shared a key K2 with Bob, and then it would encrypt the message with K2 to Bob. And then all Bob knows is that the message came from the router 2 and is decryptable by him since he has the key from router 2.
Oh, so it's kind of like I guess a good example, like a wallet tumbler.
Yeah, that's a good way of thinking about it. But yeah, the original concept is called like a mixed net. And so I just wanted to show an example of what that looked like. And it's pretty cool that we can like build this really complicated, and I think there's actually mixed nets used in like modern systems all over the world. And they're all derived from these building blocks that we've just discussed in the first half of this lecture. So I think that's really exciting. Okay, so that concludes the first half of lecture. I'm going to stop and take another 2 minutes to answer any questions with the first half of lecture, including course policies. Then we're going to take a 5-minute break, and then we'll get into the second half of the lecture. So I'm setting the timer for 2 minutes. And any questions about either the course policies, the Slack, or the first half of lecture, please throw them my way.
So regarding getting the extra credit, so you'd have to send me the link to the Slack from what I see from the syllabus.
Oh, have you not?
Right.
Yeah, yeah. Well, do you have? It's the same Slack I sent earlier, but I'll resend it in the chat.
Oh, okay. Okay. I see.
Yeah, so you should be able to join that there. You can also email to me on the anonymous feedback form posted on the course website. You'll just include your name in the anonymous feedback form so I know who is messaging me. Yeah, so I see a question from Marglen. So Bob won't know who the message came from. Yeah, so great question, Marglen. So that does mean that the message cannot be traced back to Alice. So there's no way for Bob to trace the message back to Alice. Great question. How involved with the proofs for the homework? Um, Great question, Jared. If you kind of see, you kind of getting a sense throughout that first half of the lecture how complex the proofs I'm demonstrating in class are. And I will never ask you to make a proof more complex than that. I'm going to be exceedingly reasonable, I promise, when it comes to these proofs. So you can't just say, you know, you couldn't just say, I know it's true, period. But as long as you're making the reasonable assumptions that I'm sure you'll all make. And in the first homework, I'll probably include an example of a proof for homework 1. But for now, just homework 0 is out. I'm kind of waiting for Blackboard access before I post homework 1. All right, it's been a couple of minutes, so I'm actually going to give everyone a 5-minute break. I'm going to get up, stretch, drink some water, and then we'll all reconvene at 6:50 for part 2 of the lecture. Thank you so much. I'll see you all in a moment. All right. We're back at it, everyone. Um, so the second half of this lecture will be discussing stream ciphers. So let's get started. So we just introduced and reviewed the concept of semantic security, but we referred to the actual underlying cryptography systems rather obliquely. And while we have a comfortable understanding of some of the mechanisms and requirements around semantic security, we have not actually defined a real cipher that meets its requirements using short keys, right? We have defined the one-time pad, but the one-time pad uses really long keys. So we need to think of a short key system now. So the primary challenge of using short keys of length L to derive longer keys that allow us to encrypt messages of length L. That's kind of the primary challenge. And the way we're going to solve this challenge is using a primitive called a pseudo-random generator. Now, a PRG can be described as a function G that takes in a key of length L and outputs a new key of length capital L, where capital L is a longer length. Here's what a modified one-time pad would look like based on a secure pseudo-random generator. Any questions on what a pseudo-random generator is? The reason we can't use a fully random generator is that a fully random generator will take, is just mathematically does not exist. Like even if you had a number in the sky that wrapped around the entire world and you could just select random slices of it, even that wouldn't be truly random. We literally could not keep a truly random function in memory in a computer ever mathematically. So that's why we can't use a truly random generator. So we have to settle for these pseudo-random generators. So any questions on what a pseudo-random generator is, or why we cannot use a fully random generator, why we need to resort to pseudo-randomness? I'll wait 30 seconds. So great question, James. So and I think Jared has a similar question. So the reason we cannot use a truly random number generator is that they do not exist, right? Like when you use a random function on your computer, that's not a true random function. So for something to be truly random, its space would need to be the entire universe. And it just is not, it's not possible to store that in memory. If we could store it in memory, we could solve all kinds of mathematical problems that we cannot solve. And it has to be pseudo-random because we are unable to use true randomness. This is a nice approximation that we can use. Okay, great. So I'm going to keep moving forward. Thank you for the questions. So here again, kind of fleshing out the modified one-time pad using a pseudo-random generator. So we use G of S as opposed to the original key K. And S, you can think of that as secret. So let's discuss the security of the modified one-time pad. The security rests on whether or not G of S can be distinguished from K. And what's convenient is that if we can prove this to be true, then we inherit the semantic security from the original one-time pad. So we wouldn't need to reprove that, which is really convenient. I can sense some questions in the air about why this is the case. And I think that's something I'd like to go over in office hours. It's a little bit of an advanced concept for this kind of this first initial context. So any questions about this idea? Happy to address them now if people are really curious. Any questions about this? About G and S and L and one-time paths and semantic security? All right, great. So we'll keep moving forward. So just like how in semantic security, we played security games with pseudo-random generators, we're going to be playing security games. So let's let S be the set of secrets composed of 0 and 1 of length little l, and let K be the key space big L such that L is less than little l. And let's let our adversary A be computationally bounded. If experiment 0, the challenger samples S from S uniformly at random and generates G of S equals K and sends it to A. If we're in experiment 1, the challenger will sample K from message space K and send it to A. So in experiment 0, we're using the pseudo-random generator, and in experiment 1, we're using the truly random generator. A returns B, guessing which experiment the challenger conducted. And if it is a truly, and if the PRG is a secure PRG, then it will have negligible advantage. So the advantage will be 0 or 2 to the negative 100. So the concept here is that this is the security game we would play to determine whether or not a pseudo-random generator is secure. Any questions on this game? On the sampling techniques, on the experiments? And again, I'll rework these slides a little bit so that WB, so I clarify this WB probability question that was brought up in the first part of the lecture. I'll wait 30 seconds for questions. I know this is like a big concept. I want to give everyone some time to process it. Can I explain what the S is again? Sure. So the S is the secret, and it's the input to the pseudo-random generator. So you can think of S as maybe a string of length 5, and S is passed into G to produce a K, and that K is of length capital L. So let's call that length 28. So the pseudo-random generator takes 5 and produces 28. Great. Thank you, Stefan, for asking the question. Okay. We'll keep moving on then. So here are the takeaways that I want everyone to have from PRGs. If we have a secure PRG, then we can encrypt messages efficiently, given a key shorter than the message. We don't know actually if PRGs exist. If we prove that they exist, and demonstrate that P equals NP, that is the space of polynomial problems is equivalent to the space of non-polynomial problems, which would be, that would break security. That would probably change our world quite a bit. And this is the bulk of cryptography. We assume certain problems are hard, and then we use those hardness properties to develop secure protocols. So now let's get into some real world examples of when people have encrypted PRG, when people have implemented PRGs and they've done it incorrectly, and that's caused problems. I hope this serves as motivation to, if you can avoid it, never implement your own security. So content scrambling system, DVDs. I feel like this is one way in which I've aged myself in the sense of I grew up with DVDs, and that might be dating me a little bit. But DVDs used to be encrypted. So if you were to steal information from a DVD, you'd have to break the encryption. And the idea behind this content scrambling system, or CSS, is to approximate a pseudo-random generator by using linear feedback shift registers, or LFSR. Now, these are their own concept. They're quite interesting, but basically what you do is you hold, you have 4 registers, hold the number in each register, and then shift them around over time. This is a very weak approximation. And the disadvantage was compounded by the fact that it was illegal in the United States when this was invented in the 1990s for manufacturers to export cryptographic systems with keys exceeding 40 bits. And I wonder which US government actor is interested in people not having strong encryption. I wonder if the NSA has a vested interest in people not having strong encryption. This is an example of where like policy led to weak cryptography. And it's a good lesson for us to remember that we need good rules and good regulations. But when the incentives of the government are misaligned with the incentives of the people, this is an example of what might happen, which is really interesting.
Is that law still the case?
I believe that law was overturned. Most of our modern encryptions have key bits of 128 to 256, but that's a
Yeah,
great
that's what I
question.
was thinking. I was like,
Yeah. Along those lines, I'll throw this out there. They're actually illegal programs. And if you have a T-shirt with the binary of the programs printed, that's technically an illegal T-shirt because it's a record of that program, which is kind of a crazy concept to think about. If you're interested in these kinds of how does policy overlap with cryptography and computer science, I would love to talk to you in office hours about that. I actually taught a course about it, a couple of years ago. So it's one of my favorite areas to think about. So really interesting stuff. Anyway, back to maybe how you break this code. So the really basic concept is you use the stream of output bytes and the outputs of one of the smaller LFSRs to obtain the output or to derive the output of another one of the LFSRs by kind of brute forcing it. And since the smaller LFSR is smaller than the actual size of the key, you can check if the output matches to validate. Instead of brute forcing a 2 to the 40, you're brute forcing them like 2 to the 16. And it's better than brute forcing the whole key. By 1999, and keep in mind this implemented in like the 80s, I think, the full key recovery attack ran in like 18 seconds. And that's using hardware from the 1999. Our phones are more powerful than hardware back then. So you can imagine how easily we break this cryptography today. There's a great article in Wired linked here. So if you click this little hyperlink here, that'll take you to the article about it. Other examples, GSM encryption. This is cell phone encryption, uses 2 LSFRs, and they tried to keep this design private, but it was reverse engineered pretty easily and attacks were found. This is a good lesson here. Never rely on security through obscurity. Never rely on your system being secure just because no one knows how your system works. People will figure out your system works, then you'll immediately be broken it too. The Snowden documents reveal that the NSA can process data encrypted with the A51, which uses 3 LSFRS. Yeah, using them to store keys. Yeah, it's true. They'll never be able to exit them. So the Snowden documents reveal that the NSA can process data encrypted with this encryption standard. Important to know that like there were known attacks on the protocol well before the NSA was known to have cracked it, but like still pretty crazy. The NSA was like breaking these encryption codes, and it took like Edward Snowden to leak them for us to find out. Bluetooth E0, which is another encryption scheme, uses 4 LSFRs, and that's been broken as well. The RC4 cipher, used in SSL or TLS, also relies on LSFRs and has also been broken, although not as badly as other ones.
Can you repeat
Uh,
what a LSFR is? Sorry to interrupt.
Yeah, so they're so a linear shift feedback register. I'll draw one on the little slides.
Is it kind of like a bitwise shift?
Yeah, it's exactly the way to think about it. When I draw a shape, just because I like drawing shapes, and a very useful way to approximate these. So here's register 1, here's register 2, here's register 3, and here's register 4. So what would happen is you would have this register. Oh, that's terrible. Go to this register, go to this register, go to this register, and then for this register, this would actually be the compound of this one and this one combined. And so you can imagine that as you cycle, right, you copy this value to here, this value is copied to here, this value is copied to here, and then these two values are combined and copied over here. So that's kind of a concept of a linear feedback shift register. What's nice is they're really easy to implement and like can be honestly be done with just using hardware, which is kind of the appeal of them. But they are not good approximations. And if you think about this, if you do this like 100 times, this column right here of blocks can be used as a pseudo-random text output. So I'll kind of demonstrate that here. So there's a second row. Here's the third row. And you would take this kind of last column and you would maybe, let's make them brown. You would take this last column and that would be your random string generated by the PRG. So right, the PRG is implemented by this linear feedback shift register. So this is just an example of like where security was implemented really poorly and it had massive repercussions on like $1 billion industry, which is really fascinating. That's the end of lecture today. If you remember our first lecture, we went for an hour. Today we went for an hour and 30, 40 minutes. And I'm going to keep pushing the length of the lectures until we find a point that feels uncomfortable.